Welcome, everybody. Thank you for joining us. My name is Lori Cook, and we're going to be talking about the 2015 and 2018 NDS example problems document today. We're specifically going to go through a few examples on member designs and a few examples on some connection basics. My name is Lori Cook, and we're going to kind of breeze through some of this copyright material here. And this is an accredited presentation. Our learning objectives today are shown here. I'm going to assume that everybody took a look at these when you signed up for the class, so I won't dwell on them too long. The primary focus of today's presentation is going to be the NDS example problems document, but we will have references, obviously, to the NDS and the NDS supplement as necessary. Before we jump into everything, we'll start with our first poll question. And this one's the easiest one because there's no wrong answer.
All right, sorry about that. The launch was giving me trouble. All right, as usual, this one's the easiest. And we found out this morning that there seems to be a little lag for a lot of you that are working from home, so we'll be giving a little extra time for the poll questions. All righty, I'm going to close. So we have 77% engineer, 15% code official, 4% architect, 3% builder, manufacturer, or other, and 1% fire service. No matter your profession, we are delighted that you are here today and hope that you find something of value. We're especially glad that you're here and getting your mind off of everything that's going on around us.
All right, great. We got a pretty broad variety of folks present today, so that's good to hear. So you might notice today I'm working from a PDF document as opposed to my standard PowerPoint document, but I think that we'll still be able to have everybody see everything clearly and get the information across clearly. So, but if you're noticing that I'm scrolling as opposed to flipping through slides, I just wanted to point that out. Our outline today, we're going to start by talking about the example problem document just briefly to introduce it, and then we'll jump into the slightly more interesting part. That'll be the design examples. There'll be 3 examples where we're going to do some member designs. So there'll be an example where we do a beam, a column, and then a member that's loaded about multiple axes. After that, we'll finish with some connection design examples, and there'll be shear examples and withdrawal examples. And if you've printed these slides out at home, I had a typo on this slide, so you'll just want to adjust that last bullet point there. And if we have some time after that, I'll spend some time talking about some of the resources on AWC's website that some folks might not be aware of, but that we find very useful. And then we'll close it out with some Q&A. So please be sure to stay for as close to the full 90 minutes as you can. As I mentioned, the documents we're going to be talking about today, primarily when I'm discussing these examples, I'm going to be referring to the 2018 NDS for section references and equations and things like that. They are going to be the same as they are for the 2015 NDS for nearly every example that we do today and nearly every example in the actual document. There is one example that we'll do today that is going to apply to the 2018 NDS only, and I will point that one out when we come to it. And that's just because there are some provisions that were added in the 2018 NDS that were not present in the 2015 NDS, so we will discuss that when we come to it. This example problem document is relatively new. It came out in the latter half of 2019, so it's one of our newer documents. It's available for download on our website, and we'll take a look at where you can get that later. And you can also purchase a hard copy of it if you're interested. So we'll start by just with our simply supported beam, and let me zoom in a bit here so it's a little bit more clear. There we go. I think that's. So the way that the example problem document is laid out is the examples are numbered, so that's why you see this E1.2A. That's the number on this particular problem. When you go into the document, that's how they're labeled. They're each is numbered. And for this particular problem, we have a select structural Douglas fir beam that's a 4x16. And just a moment here, my screen's a little, there we go. It didn't want to scroll for me. So what we're going to do, we have a 20-foot span on a beam, and we're assuming that it supports a hoist that's located at mid-span. And we want to determine the maximum allowable load that this hoist, including the beam self-weight, can hold. We're assuming that's a normal load duration. And we're assuming that the beam is supported on 2x4 top plates at the supports. So that will come into play when we look at our width of bearing and things like that when we're doing our bearing checks. We see that we've only got lateral support at the ends of the members. The ends are considered pinned. And for this example, we're assuming that this is an engineering span. So we're assuming that the span is center to center of support. One other thing I do want to point out is that we've simplified some of the load combinations, the load cases in this example. So we're not doing a full ASCE7 analysis of every load combination. So you can check NDS section 144 for some more information on that. But this is just going to check some of the load combinations. So when we go into the NDS and we start designing with solid sawn lumber, for this example, we're going to be designing with Douglas fir larch. We start with the NDS supplement, which provides unadjusted design values for a variety of different species of lumber. For this example, we need to go to table 4A, which is the reference design values for visually graded lumber that's 2 to 4 inches thick. So that's nominal 2x material and nominal 4x material. Douglas fir larch, you can see we're using a select structural grade, so that's this first row here, and all these values are going to be reflected in the example problem as we go through the calculations. So this is where these numbers are coming from. They're all expressed in pounds per square inch. So these, again, are the unadjusted values. So as we go through this problem, we're going to use the adjustment factors from table 431 in the NDS and determine the appropriate design values for each of these different stresses, bending stress, tension, and so on. So again, here's our problem statement, just restated. So we start by defining, and these problems are all worked out in MathCAD, so you might notice that there's a colon next to the equal sign. That's just some MathCAD notation for when you've defined a value. The values here are again pulled from table 4A of the NDS supplement. We've got F sub B is the bearing stress. F sub C perpendicular, or F sub C perp, is the compression perpendicular to grain. E is the modulus of elasticity, and E sub min is the minimum modulus of elasticity we use in some of our equations for some of the calculations. And then F sub B is our shear stress. We then use the adjustment factor specified in table 431, so that's going to include C sub D, which is our load duration factor. And when we say a normal duration, that's equal to 1.0, or a load duration for a typical dead plus live combination. The C sub FU factor is a flat use factor. For this specific beam, the member is not loaded along the wide face, so the flat use factor would not apply. So we simply set that equal to 1. Everything else in the problem statement leads us to conclude that our moisture or content would not be above 19%. So our C sub M, our wet service factor, is equal to 1. Our C sub T is a temperature factor. We're not using elevated temperatures. That's also equal to 1. This is not a repetitive member, so we're not using a C sub R, an increase for a C sub R. And it's not incised, so C sub I is also equal to 1. C sub capital T here is the buckling stiffness factor. That's sometimes used in truss designs and things like that, but it does not apply in this example, so we're not going to have any adjustment due to that, so that's equal to 1. And then the C sub F is the size factor, and that's also in table 4A, where we can find that. And for a beam that's 14 inches and wider, like we have, the size factor is equal to 1.0. Using the equations in table 431 and the adjustment factors, we can calculate the modified modulus of elasticity, this E prime, and that would be our design value, our adjusted design value. We can do that for the modulus of elasticity, the E value, and the E sub min value. So we can get the adjusted design values for that. But to calculate the adjusted bending capacity, the F sub B prime, we need to calculate a beam stability factor. So we need to go through some exercises to do that. Laying out the geometric dimensions and properties of the member, we have a length of 20 feet. The actual dimensions of a 4x16 material are 3.5 by 15.25 inches. This W sub bearing value is the width of bearing, and we'll use that when we do a bearing compression check at the end, so that is an important factor, and it's not necessarily noted with its own variable in the NDS, so that's just what we chose in this example. Some cross-sectional properties, the area, the section modulus, the radius of gyration, they're all available both in the NDS supplement, or you can calculate them if you want to flex your MathCAD skills like we did here. And again, they're tabulated, but it's the same either way. So to calculate the beam stability factor, first we need to calculate F sub B star, and that's the adjusted bending design value with all of your adjustment factors except for the beam stability factor and the flat use factor. So F sub B star, we have the unadjusted reference design value, our F sub B, multiplied by our load duration factor, our wet service factor, temperature factor, size factor, incising factor, and our repetitive member factor. We get our F sub B star value, and then to figure out the C sub L, we need to go into table 333 and determine the effective length. So that's based on not only the depth of the member, but also the laterally unsupported length. So for us, that's the full length of the member, which is 20 feet or 240 inches. So that L sub U divided by D gives us a ratio, which we then go to table 333, which will provide us with the equation necessary to calculate the effective length here, which we see is 375 inches. What that number actually is not necessarily super important, but you do need it to calculate this slenderness ratio for bending, this R sub B value. Calculating that is then plugged into the critical buckling design value, this F sub BE, which we use then in this equation for C sub L, which again is your beam stability factor, adjustment factor. C sub L for this beam is equal to 0.876. So we multiply that adjustment factor and the flat use factor, which was just equal to 1.0, by that F sub B star, because remember, F sub B star was the adjusted design value except for these two factors. So multiplying this F sub B star by those two factors gives us our adjusted bending design value, F sub B prime, equal to 1,313 PSI. Whew, but we're not done yet, right? We have to now determine what is the maximum total moment that this member can support. So that's going to be based on our formula. We're going to reach way back to our mechanics of materials class in school, and our bending stress is equal to the moment divided by the section modulus. So if we rearrange that formula, we can determine the maximum moment based on our section modulus and our allowable design stress. So we calculate a maximum moment for this beam, and that's the total moment. So we need to account for not only the applied load, but the self-weight of the beam. So this next part, we use a little bit of engineering judgment, and we assume that the load for the beam weight is based on a density of 37.5 pounds per cubic foot. And this is a little bit high. It's a little bit conservative. So this value is 110% of the tabulated value for the specific gravity of southern pine. So essentially that can account for any variation that could occur within different materials. You know, there can be variation in specific material depending on where it was grown and how it was harvested. So this is it's not in the NDS specifically. This is one of those times where engineers, we use our best judgment and determine, what we think is an appropriate value. So in this example, we determined 37.5 pounds per cubic foot was probably conservative, but we were comfortable with that level of conservatism. It gives us a beam weight of 13.9 pounds per lineal foot. The moment that is induced by that self-weight is just based on the formula WL squared over 8. So that's what this takes the shape of here. And we get a moment based on the beam self-weight of 695 foot-pounds. So the allowable moment due to the applied hoist load would be whatever capacity is left. So the allowable moment in this case, we take the difference between that maximum moment and the self-weight, and we get an allowable moment of 14,154 foot-pounds. So because that hoist is applying that load at midspan, the moment induced by that point load at midspan is equal to P times L over 4, or the point load times the length divided by 4. Again, we just rearrange that formula and we can determine that our allowable concentrated load at midspan is 2,831 pounds. So with that as our maximum load, we then just need to do a few other capacity checks to determine we're not exceeding the beam's capacity in any other direction. So the first check we'll do is a shear check. So the maximum shear for a simply supported beam occurs at the supports, and it in this case is going to be equal to P/2, which is the hoist load divided by 2. So we get a shear V of 1,415 pounds. Our shear stress is calculated as 3 times V over 2 times the area. So that B times D is our cross-section area. So our applied shear stress is 40 psi. Our shear capacity is based on that F sub V, that unadjusted shear stress, times the load duration factor, C sub D, the moisture factor, C sub M, the temperature factor, C sub T, and the incising factor, C sub I. So we get an adjusted value of 180 psi for the shear capacity, which exceeds our demand of 40 psi, so we're okay. We do a similar check for the compression perpendicular to grain at the bearing points. So the shear load would be applied over the area of bearing. So the F sub C perpendicular, or the applied compressive stress perpendicular to grain, is equal to the shear, the reaction load, divided by the area of bearing. So for us, it's that width of bearing times the B value, the breadth of the beam. So for this beam, that just calculates out to 116 psi of demand. Our capacity, we calculate using those same adjustment factors that we were familiar with and the reference value from the NDS supplement, the F sub C perp value. We get an adjusted capacity of 625 psi, so we are okay. I do want to point out that there is a bearing area adjustment factor in the NDS in section 3.10.4 that you can use to increase the bearing capacity. We didn't really need it in this example because our bearing capacity is 625 psi and our demand is only 116 psi. But that is something that you do want to be aware of, and we're actually going to take a look at employing that in a later example. And then our last check is a deflection check. So there are two things causing deflection, rather. There's a deflection due to the beam self-weight, and that's a continuous load. So the deflection for that is based on 5 WL to the 4th over 384 EI. So that's, I know that there's a lot of numbers in this, but that's what that equation is doing. And there's a few things that are in here as conversion factors. So this inches and foot and things like that. But that's the formula is our old friend 5 WL to the 4th over 384 EI. So we can calculate a deflection due to self-weight. We can calculate a deflection due to the crane load. Again, that was, again, a point load at midspan. So the deflection due to that is based on the equation P times L cubed over 48 EI. So you'll see that again here, this P times L cubed over 48 EI. So then our total deflection is just those two values summed. And we can calculate the span to deflection ratio and determine if it's within our acceptable limits. So our L over delta is equal to 545. So depending on your restrictions, most of the time, my designs, I use L over 360 as a criteria, so this would meet that. So it should work for most of your designs, unless you're in something very stiff where you need L over 720. So that last example was in allowable stress design, or in ASD. this next example we're going to do is in LRFD, or in load and resistance factor design. And you'll see that there's a few equations, or sorry, not even equations, there's a few adjustment factors that look a little bit different, but for the most part, the overall design process with an LRFD design and an ASD design is not that drastically different. So this next example we're going to do is a compression member analysis, or column analysis. It's a 2x6 spruce pine fir interior bearing stud. It's 91.5 inches long, sheathed on both sides with gypsum board, so we're assuming that it is continuously supported on those sides where it's sheathed with that gypsum board. And it only carries dead load and snow load from the roof. So the load combination, we're only checking one load combination in this example. Again, others may apply for your structures, but for this example, we're just going to check this one. So it's 1.2 dead plus 1.6 snow, and we're using lambda equal to 0.8. So we're going to calculate the C sub P factor, which is our column stability factor. And as we go through it, you might notice some similarities between the column stability factor in this example and the beam stability factor in the last example. We'll also calculate the allowable compression parallel to grain, the design value for that, the F sub C prime for the stud. And then we're assuming the studs are at 16 inches on center and that the top and bottom plates are the same grade and species. And we'll determine some axial loads based on both the buckling and the bearing limit states. So here as we scroll down, this is an illustration of our stud. And before too many of the engineers get too carried away on me with pointing out that yes, we're assuming a pin-pin connection, I recognize that we do have forces here and here that would occur at these pins at the end of this column. However, because it is only carrying gravity loads, these forces would resolve to zero. So we left those arrows out of the illustration just for the sake of clarity and simplicity. But you don't need to send me an email about it, I am aware. Okay, so this problem we're gonna roll through in a similar fashion as we did on our previous problem. We will first start by designing or by determining our reference design values and any adjusted design values that we need. So for this example, we're going to need the F sub C value, the compression stress. We'll need the E min value, the modulus of elasticity, and we also need F sub C perp, the perpendicular to grain compression stress, and those are all in NDS table 4A. Our adjustment factors are, like I said, some of them are exactly the same as in the last problem. So that C sub M, moisture adjustment factor, or I'm sorry, the wet surface factor. C sub T is the temperature factor. So those are just set equal to 1.0. C sub F is our size factor, and that's from the NDS Supplement table 4A. Our incising factor is equal to 1.0, and that buckling stiffness factor is also equal to 1.0. We have this lambda factor here. That's an LRFD only factor, so that's why we didn't see it in our previous design. We also have some K sub F factors, and there's a different K sub F factor for each of these different design parameters. So we've denoted the K sub F factors with a subscript. So this K sub F sub C is the K sub F, or the K factor rather, if not K sub F, the K factor for the F sub C value. This not lambda, I'm messing up my Greek letters, I'm sorry. This phi sub C is the phi value associated with this compression stress, F sub C. We have this case of E-min factor for obviously E-min and a similar phi value for that. And then again, one for the compression perpendicular to grain, the K sub C perp and phi sub C perp. Our E sub min prime is our adjusted E min value multiplied by our various adjustment factors. So you can see which of those applied here. And again, that's in NDS table 431. Some of these LRFD values come out of a table in Appendix N as well. So if you're not sure if something is not in table 431, you may need to refer to Appendix N. But we can calculate our adjusted E min factor, and we can calculate our adjusted F sub C perp factor based on the adjustment factors that we've got. So the last one we'll need to calculate, though, is our F sub C perp, our adjusted, or our F sub C prime, I'm sorry, our adjusted compression stress. And to do that, we need to calculate that column stability factor. So laying out our member geometry, the length is 91.5 inches. Our member is a 2x6 nominally, so its actual dimensions are 1.5 inches by 5.5 inches. The column stability factor, we start our calculation with this F sub C star. It's the adjusted compression design value with all the adjustment factors except the column stability factor, the C sub P. So we use the value from the NDS supplement, the F sub C, and then our adjustment factors as we've defined earlier. And then we need to check the effective, we need to determine rather the L sub E, the effective lengths of compression for the member in both planes of lateral support. So that's the strong axis and the weak axis. And in this one, the strong axis buckling will control. In that we are assuming that the gypsum braces the member continuously along the weak axis. So the L sub E2, our weak axis buckling, our unsupported length is equal to 0. For the strong axis, our unsupported length is equal to L, or the full member length. So that's that 91.5 inches. So we are going to focus solely on the strong axis buckling because this weak axis becomes irrelevant with this L sub E2 equaling 0. But we're using the subscript 1 to denote the strong axis buckling. We need to check the aspect ratio, or I'm sorry, the L over D ratio. So if L sub E1 over D is greater than 50, then the column or the compression member is too slender. There are provisions where that number can be higher during the construction phase, but in general, your design, you need to have an L over D ratio less than 50, and that's in NDS 3.7.1.4. So really, you really want to remember is that the L over D ratio is limited to 50, and that's a slenderness limit. So we use that L sub E over D value to calculate this F sub C E, which is the critical buckling design value for compression members. And using this F sub C E value and this C factor, which is simply pulled out of the NDS, it's a constant for sawn lumber equal to 0.8. We can plug these into the column stability factor equation, which is, you can see expressed here. So for this example, our C sub P is equal to 0.703. Again, we can simply multiply that C sub P by our F sub C star because that had all of our other adjustment factors in it, so no need to reinvent the wheel. And we can get our adjusted compression design value, our F sub prime C of 1537 PSI. And then we just determine our axial loads based on our 3 different limit states. So we have a buckling limit state, we have a perpendicular to grain bearing, and we have a parallel to grain bearing. And so those are all going to be based on the relevant F sub C times the area. So the area is simply equal to B times D. Our buckling load is equal to F sub C prime times the area. Remember Euler buckling? I know some of you just cringed in your desks. But that's our buckling load based on our axial load based on buckling is 12,683 pounds. Our perpendicular to grain bearing would be the area times the F sub C perp prime, the adjusted compression perpendicular to grain value. And that's going to equal 5,270 pounds. And then we have a parallel to grain bearing value where we use F sub C star times the area, and that gives us a bearing of a capacity of 18,034 pounds. So in this case, we see that we are limited by this perpendicular to grain bearing. And in this case, it's limited to 5,270 pounds. However, we talked about we have that bearing area factor, that C sub B, that we can use to increase the bearing controlled load on interior studs. And this bearing factor is 1.5 for the 1.5 nominal bearing length measured parallel to grain is equal to 1.25, that 1.5 inches. So we can multiply that piece of bearing perpendicular to grain bearing value by 1.25 and increase the capacity by 25%. So we've gone from being limited to 5,270 pounds to increasing the capacity to 6,587 pounds, and that becomes our controlling value. And then if you're using a 3-to-1 snow to dead load ratio with this limit, that would translate to a snow load of 3,294 pounds and a dead load of just shy of 1,100 pounds there. So that's an example of where that bearing area factor can be useful. So we didn't really need it in the last example, but in this example it was helpful. Whew, all right, I'm gonna take a break from talking for just a moment so we can take time for a poll.
All right, I think we all probably need that break. So let's see, the aspect ratio, length divided by depth of a compression member needs to be less than 50. Is that true or false? All right, I've got almost 80%, so I'm going to go ahead and close.
All right.
If I can find my mouse. Oh my goodness, it just runs around on me. All right, so let's see. 91% say true. So what do you say, Lori?
91% of you got it right, so that's great. It is true. So that's that slenderness ratio I mentioned in the last example. So it probably would have been better to word the question as the slenderness ratio of a compression member needs to be less than 50, but 91% of you understood what we were asking for. So, and as I mentioned, there are limited situations where you can go up to 75 during construction, but in general, in service, you are limited to no more than 50. All right, so those first two examples we were looking at were members loaded about one axis only. So this next example, we're going to do a combined bending and axial tension example. So we are loading this member about two different axes. So this is an example where we're assuming it's a truss cord member. It's a nominal 2x8 hem fir, and it's going to be used for a 12-foot member between panel points. We're assuming that the member has a uniform dead load of 8 psf, and then we have tension forces running along the length of the member that are equal to 880 pounds from wind loads, 880 pounds from a roof live load, and 1,420 pounds from dead loads. The trusses are spaced at 4 feet on center. Our framing will have a 19% maximum moisture content, so that indicates that our C sub M factor, our wet service factor, can be equal to 1 because we won't be in a wet service situation. So what we want to do is check the adequacy of the bottom cord for bending and tension, checking multiple load cases. So this is an example where we are going to check a few different load combinations, but again, there's a lot of load combinations in ASCE 7, and if I went through all of them, you guys probably would be here for a lot longer than 90 minutes. So we're only going to check 3, but I think that these will be, illustrative of the various points we wanted to make. So again, we're starting with our reference design values for hem fir and our various adjustment factors. We do notice that we have a size factor equal to 1.2 for this one, so we get a bit of an increase on that. Our member geometry, again, for nominal 2x8 is 1.5 inches by 7.25 inches, and that is in the NDS supplement. Our gross area, or our cross-sectional area, is just B times D, the breadth times the depth, and we're going to use the S value, the section modulus. Taking a look at our applied loads, we had that dead load of 8 pounds per square foot, with our trusses being spaced at 4 feet on center. So our tributary width, or this W sub trib, as it's noted here, is 4 feet. The rest of the loads we're looking at are all tension loads. So these are all resolved into forces already that act along the length of the member. So our wind load would be 880 pounds. Our roof live load is also 880 pounds. And then our dead load is 1,420 pounds. So the first load case we're going to look at, the first load combination, is a dead plus roof live load plus wind load combination. And the load duration factor for this load combination would be 1.6, and that's based on that short-term wind loading. So we get that increase based on the short-term loading. We're first calculating our adjusted tension parallel to grain design value. So again, just starting with that unadjusted value and applying the appropriate adjustment factors. This is an ASD design. I don't know that I mentioned that earlier, but so we will be using, obviously, the load duration factor, or C sub D, as opposed to the K factors and the lambda that we used for an LRFD design earlier. But so checking our tension loads that are applied along the length of the member, we can calculate an allowable tension parallel to grain design stress of 1,008 psi. Our combined tensile loads for load case 1, as noted here, this T sub 1 would be 3,180 pounds. So to convert that to a tensile stress, we need to divide that T sub 1 value by the area, and we get an applied actual tension stress of 292 psi, which is less than our allowable adjusted value. So that's okay, that's good. So next we need to check our bending for the member for the applied self-weight or applied dead load rather, as well as any other bending forces. So again, we use our F sub B star value to determine the beam stability factor. So I won't go through all of as one of my favorite professors used to say, I won't go through all the blood and gore that is all the math on this page, but we do see that our beam stability factor is equal to 0.404 for this particular member. And then we also see that in this example, we calculate something called F sub B star. It's denoted with 2 stars. And that's something that you might need to use if you're calculating a glulam member capacity. So that's why it's actually included. It was included in this MathCAD analysis because we can use it to apply glulams if we need to with minimal modifications. But for this example, it's just equal to F sub B prime because we don't have a C sub V factor. So that's a roundabout way of saying that our F sub B prime and our F sub B double star would be the same value. So the bending in this example, the moment comes from the dead load. So the maximum moment is calculated based on that 8 pounds per square foot times that tributary width of 4 feet. So again, WL squared over 8 is that formula that we learned back in our mechanics of materials class back in school. So that's all that this is using is just WL squared over 8. And that's our moment due to the applied dead load. So calculating our bending stress, it is equal to M over S, remember, maximum moment over the section modulus. And our applied bending stress is 526 PSI compared to an allowable of 660. So we are not exceeding the capacity in bending either, so we're doing good. But we do need to do a interaction check next. So that's a combined bending and axial interaction. And what this does is it makes sure that we're not overstressing the beam with the combination of both the bending and the tension loads. So if the axial tension is using 50% of the beam's capacity, then you only have 50% left to support the bending loads. So these equations, these interaction checks just come from equation 3.9-1 and 3.9-2, and they both need to be less than 1. And in this case, they both are less than 1, so that's good. So we're okay. All right, we're going to check the next load case. This is the dead load plus roof live load. Now, the important thing here to note is that this is a roof live load, and that's considered a construction load. So in this instance, our load duration factor would be equal to 1.25. The rest of this analysis for this load case is largely the same as load case 1. We check the tension capacity based on the live and the dead loads, and we can calculate our adjusted tensile capacity of 787 psi, 787.5. And then our applied tensile load for the live and dead loads is 2,300 pounds. Resolving that into a tensile stress, we see that our applied stress is 211 psi, our allowable is 787 and some change, so that's good. We're not exceeding the tensile capacity, but we do need to check the bending stress now. So the bending stress, the bending capacity would be checked the same way. We base it on our F sub B star calculation and our C sub L. Once we figure those out, we get our allowable bending stress, our F sub B prime of 649 psi. The moment that, in this example, the F sub B would not be different from the previous example, or the previous load case, I'm sorry. So it would still be 526 psi because it's still using that WL squared over 8 equation, and the W is still that 8 pounds per square foot times that 4-foot tributary width. So it's the same bending stress due to dead load here, and our capacity is 649 psi, our adjusted capacity. So that's okay. Checking our interaction check again, we're still less than 1 for both of these checks, so that's good. So it works for a dead and a live load. And then the last one we're going to check is a dead load only. So for a dead load only, we see this one, we actually have a reduction in capacity due to the load duration factor. So our C sub D is equal to 0.9. Our applied loads are again only due to dead loads. So we have a tensile load of 1,420 pounds per square foot. Compared that to our, we resolve that into a tensile stress of 131 psi. Our allowable design stress, our F sub T prime, is 567 psi. So we're not overstressing it in tension. Same deal as before for bending. We do have to calculate that C sub L once again, but we're seeing that our F sub B prime is 619 psi. Once again, in excess of the demand of 526 psi due to the dead load moment. And then checking our combined bending and axial tension, we see that we have both values less than 1.0. So, and it is actually quite interesting to note that our bending and axial tension interaction values for dead load only are substantially higher. This one is 0.8, this one's 0.64. If we go back and look at our dead and live, these ones aren't quite as high. And then also, if we look at the interaction check for our dead plus live plus wind, these ones you can see are 0.61 and 0.35. So even though the actual capacity or the actual values of the loads might seem higher, it could be that the dead load, for example, could actually be your controlling interaction. So that's just an example, again, of why it's important to check all of your load cases. Okay. All right, so now let's talk about some connections. We've gone through some member design examples. The next few examples we're going to do are going to be some connection basics. So the first one we're going to do is the example I alluded to earlier, where I said we had one example that applied to the 2018 NDS only, and you can see that here in the title of this example problem. This is a roof sheathing ring shank nail, or an RSRS nail. So these fasteners were added to ASTM F1667 prior to the release of the 2018 NDS, and that's the standard that the NDS references for nails. So these are a standardized nail. They're not considered proprietary, and they also accompanied the addition of the new provisions for fastener head pull-through. So we're going to do this analysis based on the 2018 NDS provisions, where we do need to check fastener head pull-through. So this is not something that would apply to the 2015 NDS, because those fastener head pull-through provisions were not in the 2015 NDS. The fastener head pull-through provisions are only in the 2018 NDS. So that being said, this is going to use the provisions from section 12.2, and this is an ASD example, allowable stress design, and we're going to calculate only the reference withdrawal design values. So we're not going to get into any sort of adjustment factors or anything like that. In this example, we're only trying to calculate the reference design value. You can see our main member here, we're assuming is a 2x6 Douglas fir larch member with a specific gravity equal to 0.5. Our side member in this example is a wood structural panel that is 5/8 of an inch thick. Again, we're assuming a specific gravity equal to 0.5. The fastener dimensions, the actual nomenclature for these roof sheathing ring shank nails are like what you see here, this RS-05, or you'll see them referred to as a dash number 5. So that's just how they're called. It's a little different than the 8-penny, 10-penny that we may be used to, but this is a new product, so that's all right. The fastener dimensions you can find in the appendix, in Appendix L, for these roof sheathing ring shank nails. That's in table L6. The total length of this fastener, of this nail, is 3 inches long. The diameter is 0.131 inches, and the head diameter is 0.281 inches. A very important value is this TL value, which represents threaded length. And in this case, that's the length of the shank of the fastener that is the deformed portion, or for this example, it's a ring shank, so that's where the rings are. And this is something that applies to all deformed shank fasteners. You only use the withdrawal provisions for the portion of the shank that has the deformations in it. So even though you can tell that there is additional main member penetration of this nail, where we have this smooth portion of the shank along here, that is not included in the withdrawal calculation. So let's go into some of the numbers and you can see what I mean. So we're just defining some of the fastener geometry here in MathCAD, so you can see the diameter, the head diameter, and the deformed shank length are noted. The net side member thickness, or this T sub NS, is in this example is just the thickness of the wood structural panel. This could be the same as your actual side member thickness. If you have an example where you're boring out part of the side member to countersink your fastener, for example, then that would be resolved with that net side member thickness being a little bit smaller. So that's what we mean when we say net side member thickness. Specific gravity was equal for the main and side members of this equation on this connection, so it's just equal to 0.5. And checking the fastener withdrawal, we see the NDS equation 12.2-5 is applicable for this one. It's based on the specific gravity of the main member. In this example, it worked out that they were both the same, but really you want to pay attention to this. This is the main member specific gravity, not the side member. So if they are different, you use the main member specific gravity. And then the D is simply the fastener diameter. So we plug those in, we get a reference withdrawal design value of 59 pounds per inch. And we can compare that to the tabulated value from table 12.2e, and they are the same. So that's good, we're consistent. Remember, though, we're only multiplying that by the penetration of the shank that is the deformed portion. So in this example, that's that TL value. So we multiply the W, that 59 pounds per inch, times 1.5 inches, which is the TL, and we get a value of 88 pounds of withdrawal resistance. We next need to check the head pull-through for the fastener. So that's based on the ratio of the head diameter to the side member net thickness. So it's actually 2.5 times the head diameter. So that's greater than our net member side thickness, so we use NDS equation 12.2-6A. If you're less than that, there's a different equation that will apply. This head pull-through equation you see here, it's dependent upon the specific gravity of the member, the net side member thickness, and the head diameter. We multiply that head diameter times pi, so that's actually converting the kind of important value to the perimeter of the head. We calculate a head pull-through design value of 95 pounds. There is also a tabulated value we can check in table 12.2F. So for this example, our fastener head pull-through of 95 pounds is greater than the withdrawal design value, so that 88 pounds from withdrawal would control this fastener's capacity. And again, remember, this is the unadjusted design value. So if we have adjustment factors we need to apply, we check NDS table 1131, and we can calculate those adjustment factors for our connection based on the end use conditions. All right, our next example is going to be another withdrawal design value example, but this is going to be for a lag screw. So our main member in this example is a nominal 6x Southern Pine member, so its actual thickness is 5.5 inches, and our specific gravity is 0.55. Our side member is a 2x Southern Yellow Pine member, so the actual thickness on that is 1.5 inches. We're assuming a 1/2 inch diameter lag screw, so we go to NDS table L2, and ours is going to be 4 inches long. So we pull the tip length out of the table as well, NDS table L2, and that's 0.3125 inches. I don't remember what the exact fraction on that one is. All right. So we've got the fastener geometry defined. So let's talk about the actual penetration into the main member, because some of that is important when we calculate the actual values for withdrawal capacity. We've defined the fastener geometry based on what's given to us in the NDS appendix. The lag screw we said is 4 inches long. Our side member is 1.5 inches thick, so that's this L sub S value. The lag screw penetration into the main member is equal to the length of the lag screw minus the side member thickness minus the tip length. So let's look at that up on the picture here. So our main member penetration for our lag screw, let's see, here we go. Okay, is assumed to be, can you guys see my spotlight?
Yep, see it.
All right, my laser pointer is up. Okay, so the main member penetration is calculated as the total length minus this side member thickness minus this tapered tip length. So that's an important thing that we want to note for lag screws, that we neglect this tapered tip for withdrawal. So going down back here again, our penetration, we calculate all those, and it sums to 2.188 inches. This matches the T minus E dimension that is in table L2. So what that T minus E dimension represents is the total thread length minus the tip length for that lag screw. So that's what that represents. And if you can be assured that all of your threads are included in the main member, then that's the value that you'll use. But if you're not sure, if, for example, you have a really thick side member and you're not sure where all the threads will be, your main member thread penetration might be less than that T minus E value. So you do need to pay attention to your fastener geometry, your connection geometry, where the threads start and stop, and where that is in relation to your shear plane. Using NDS equation 12.2-1, this is the withdrawal equation similar to the one we saw for roof sheathing ring shank fasteners. It's got a couple of fractional exponents, but we can do that. We've got graphing calculators. So we calculate a reference withdrawal design value of 436.6 pounds per inch, which rounds up to the tabulated design value in table 12.2a in the NDS of 437 pounds per inch. And again, remember, we multiply that by the thread penetration. So that for us is this 2.188. And we get a withdrawal capacity of 955 pounds for that lag screw. All right. Let's take a break and do another poll to make sure that everyone's still with us.
Sure thing. Here we go. Fastener head pull-through analysis is required per the 2018 NDS only. Is that true or false? Okay, it looks like everybody that's going to vote has pretty much voted. All right, so 70% say true, 30% say false. It's a little bit of a split there.
Well, the majority do, yeah, the majority do have it correct. It is true. So that's what I was alluding to when I was talking about that head pull-through analysis was added in the 2018 NDS. So that those provisions actually aren't present in the 2015 NDS. So if you are using the 2018 NDS or a newer version, I'm guessing, when they come out, you'll need to check that fastener head pull-through as part of your analysis for a withdrawal design for a fastener. All right. So we have one more example. I believe this is our last one, and this one's a little bit lengthy, but if you bear with me, I think we can get through it together. So this one is the last two connection examples we've looked at withdrawal design. So withdrawal is when the load is applied parallel to the length of the fastener. For this next example, we're going to be looking at a lateral load or a shear load where the load is applied perpendicular to the length of the fastener. So for this example, we have a nominal 3x Douglas fir large member as our main member, and our side member is a nominal 1x Douglas fir large member. We're connecting these two members with a 10D common nail, and you can see the dimensions there that were taken out of table L4. We're going to use a allowable stress design as our assumed design methodology, and we're going to try to compute we're not going to try, we're do or do not, there is no try. We're definitely going to compute the reference design value. So the first thing we need to do when dealing with the NDS yield limit equations in section 12.3 is define all of our inputs. And for those of you that have done one of these analyses by hand, you know that there's a lot of equations, there's a lot of bookkeeping, a lot to keep track of. So MathCAD or Excel, these are great programs that you can use to develop these equations, these analyses for these equations. So the first set of parameters we need to define are our main and side member dowel bearing strength, and these are values that just come out of NDS table 12.3.3. They're based on the specific gravity of the member. For this example, our members are both Douglas fir larch. They have the exact same specific gravity, so that makes it a little easier. We can see that our main and side member dowel bearing strengths are 4,650 psi, and we use those to calculate this R sub E ratio. The next set of inputs we're going to need are the fastener dowel bending yield strength. That's for the nail, and that's going to come out of NDS table I1, or you can also take a look at technical report 12 for some additional information on some additional types of fastenings for inputs for that. The nail diameter is specified in the appendix table. This is an assumption that the NDS allows us to take, that the length of the tapered tip for a fastener for a nail is taken as 2 times the diameter. So we assume the tip length is twice the diameter of the nail. And that becomes important when we calculate our side and main member dowel bearing length specifically. So if we looked at our illustration again, we see the nail passes through the side member fully, so that's our side member dowel bearing length is just the side member thickness. Our main member dowel bearing length we need to calculate. So let's go back down there. All right, our main member dowel bearing length is equal to the nail length, which is 3 inches, minus the side member thickness, or the side member dowel bearing length. They're equal in this example, so that's that L sub S value. And then we are allowed to include half of that tapered tip. So that's what this tip divided by 2 comes from, and that's in the NDS 12.3.5.3. You'll see that reference in there. So our main member bearing length, our main member penetration, is 2.1 inches. There is a requirement in the NDS that the minimum main member penetration is equal to 6 times the diameter. So for us, that would be 0.89 inches. We're in excess of that, so we are good to proceed. The next number we need is this R sub D value. We calculate the reduction term, and that's just in NDS table 12.3.1b. And then we get into a little bit more of that so-called blood and gore, the K1, K2, and K3 factor calculations. And these are another set of equations that I don't really like doing by hand. I find that MathCAD or Excel or something keeps track of the numbers a lot better than I can. So it's the inputs again are based on that R sub E value that we calculated based on the ratio of our dowel bearing strengths. For us, it was just equal to 1 because they were the same. And then we have our R sub T value, which is based on the ratio of the main member and side member lengths, those bearing lengths. So you can see these calculations. I won't bore you with the specifics on that. But what we do then is that we have gathered all of our inputs and we use them in our yield mode equations that are in NDS table 12.3.1a. And you'll see we have 4 different modes, modes 1, 2, 3, and 4. And in those modes, there are kind of sub-modes, I don't know if you want to call them that, But in modes 1 and 3, we have 2 checks we need to do. We need to do a main member check and a side member check. So you'll see here in our mode 1 check, we have a mode 1M check. So that M subscript denotes the main member. So this is our mode 1M solution based on the main member geometry and bearing. And mode 1 is a mode that's based on crushing of the wood if the wood is in a bearing failure. Modes 2, 3, and 4 assume some combination of either pivoting of the fastener, a plastic hinge forming in the fastener, yielding and crushing in the wood. So they're a little bit more complicated. So mode 1M is for the main member, mode 1S is for the side member. The next modes we're going to look at, the equations look a little more complicated with those K factors and such because they are modeling slightly more complicated failure modes. So you'll see the solutions here for mode 2, for mode 3M and 3S, again 3M being main member, 3S being side member, and then mode 4. What I've done here is I've just created an array with all of those yield mode solutions in MathCAD, and then that makes it easier to pick out the minimum of the value. So our minimum our minimum yield mode value in this example is based on mode 3S. That's that again, remember that's side member. So we got a value of 105 pounds. If we go into NDS table 12N, the tabulated value is equal to 105 pounds. So it's always good when our tables agree with our calculations. And once again, I do want to remind you guys that this is only the reference design value. So you would need to apply your adjustment factors based on any end use conditions. So we do have one more poll. We have some time. I am going to launch it, but after this morning's session, someone did point out to me that depending on how you interpret one of these answers, there could be 2 answers that are right. So we'll go ahead, we'll launch it, and then we'll spend a little time talking about it.
Okay, here we go. The new equations for fastener head pull-through are based on which of the following? So is that fastener head diameter, species and weight of side member, net side member thickness, all of the above, or answers A and C?
All right. Marcy, I'm not sure.
I was on mute, so
okay.
Sorry about that. 58%,
no worries.
all of the above, 36% answers A and C. Lori, I'm going to let you discuss those.
All right, so pretty much everybody is right. When we originally wrote this question, our original intent was the answer to be E, A, and C, because the species, the weight of the species is not specifically included in the equation as a mass or something like that. However, it was pointed out to me that the specific gravity is correlated to the weight, and the specific gravity is dependent upon the species. So technically, yes, B is also the correct solution. So this might not have been the best question, but I think it's good that it prompted a little bit of discussion on our part. So that's So don't go anywhere. This is the end of my PowerPoint or PDF presentation, but we do have a few more things that I wanted to show everybody. And the first of those is where on our website you can go to get the example problem document. So if you can tell I was obviously there. If you're on our publications page, which looks like this, and you can click on either the 2015 or the 2018 NDS. And if we click on 2018, we can scroll down here and you'll see our free view only downloads of both the NDS and NDS Supplement, as well as our special design provisions for wind and seismic. And if you keep going, there it is, the structural wood design examples. It is available for a free view only download as well. You can purchase a PDF copy or you can purchase a hard copy. Sadly, I did not autograph them. But they are available from our website if you're interested in getting a hard copy. And another resource we have on our website is our connection calculator. So if you go to our calculators, our calculators page, which there's a link on our homepage, awc.org, that'll take you here. And since we spent so much time talking about connections today, I just couldn't leave without mentioning our connection calculator on our website. So this is what it looks like. You can also download an app for an iPhone or an Android, as well as a Microsoft app for your Windows device. So if you're running like a Windows 10 device for your desktop, you can get it on there. We have this online calculator as well that I like to use from time to time. It will accommodate various different things through these drop-down menus. So you can see in this top one, it is available for ASD or LRFD designs. We can do a lateral or a withdrawal load. We have multiple different fastener types that you can choose from. I will point out that this calculator is per the 2015 NDS, however. So it has not been updated just yet to the 2018 NDS, and that includes those fastener head pull-through provisions. So those are not included in the calculator, but the withdrawal provisions and those lateral equations, there's lateral yield mode equations that I'm sure I made my love for those quite clear throughout the presentation. If you don't want to run those by hand, this does give you an alternate solution for calculating those. So, and it gives you many options for various types of main members. It can accommodate wood structural panel and steel side members in addition to solid sawn lumber. And it can accommodate various different end uses as well. So you can input your load duration, wet service, and temperature factors and things like that. So I think with that, we can take a few questions before we close things out. Did you want to come on, Michelle? Did we have some questions?
We have a ton of questions.
Oh man, I don't know if I'm ready for that.
Get your thinking hat on. Okay, one question came in about that last poll. Could you reiterate what you said about the answers?
Yeah, here, let's go back to that. So this last poll, like I said, when we wrote the question, we had it in mind that the answer was going to be E. It would be A and C, because the actual equation includes the fastener head diameter, it includes the net side member thickness, and includes specific gravity. So the actual weight of the side member doesn't come into play. So that was our train of thought when we wrote the question. However, when we asked it earlier, it was pointed out to me that the specific gravity of the member is dependent upon the species, and the specific gravity dictates the weight of the member as well. So, you know, the best kind of correct is technically correct when you're an engineer, and I think that you could make an argument that answer B is technically correct. So the answer could be D, even though we intended for it to be E.
Okay, good job. Okay, another question came in regarding, could you talk about clarifying the length of the fastener and using it to calculate withdrawal capacity related to deformed fasteners,
Sure.
like lag screws, wood screws, or deformed nails?
Yeah. Yeah, let's go back to that picture. Here we go. Here's a good one. Actually, you know, let's use this one. I like this one a little better. I think this makes the point a little bit better. So when we're dealing with withdrawal capacity of deformed shank fasteners, so that could include lag screws, wood screws, anything with threads or rings, things like that. We are only assuming that the deformed portion of the shank actually provides the resistance. So for this example, the main member penetration is actually, you know, this whole portion of the nail, but the deformed portion of the shank is only the 1.5 inches, the last 1.5 inches. So we would only use that value, that 1.5 inches, as the penetration that we're counting when we multiply it by our W value, which is that pounds per inch value that we've calculated down here.
Okay. Are you done?
Yes.
So go back up a little bit to that same picture. And this is a good question. Can you scroll up?
Yep.
Yeah. So say if you didn't have,
take it a second. There we go.
Say you didn't have 5/8 wood structural panel. What if you had like a 2x member that was thicker and went into the threads? So the length.
Good. Yeah, that's a good question. Let's look at our next pictures. I think it'd be a little easier to visualize on this one.
Yeah.
So in this example, the threads do actually start at the shear plane, but if, for example, if this side member was 2 inches thick instead of 1.5 inches thick, what that would mean is that some of these threads would actually be occurring in the side member.
Right.
So your main member thread penetration would be reduced. It would not be that T minus E length that we find in the NDS appendix. And that's why we did this analysis here of the lag penetration into the main member.
Yep. That's a good question. So another question came in about tip and including that in the length. How does that relate to with lag screws and nails, including the tip?
It depends on what kind of fastener you're using, and it depends on what kind of loading. And let me grab my NDS because I don't remember all of them off the top of my head. But it is in NDS 12.1 in the various sections that dictate lag screws, wood screws, and nails. So for nails, for example, in shear, we will include half of the tapered tip length when we're calculating those yield mode equations.
For bearing, or
yes,
yeah. For lateral length on the nail.
Yeah. So and then for lag screws, when we're using with lag screws in withdrawal, we do not use the tapered tip. So here we go. It's in 12.2.1.2 for lag screws, where it states we exclude the length of the tapered tip. And then, let's see, when you go into wood screws, you can use the tapered tip. So it's one of those things. How much of the tip you use depends on the type of the fastener and the loading. So you will need to go into the appropriate NDS section for the type of fastener and that load. So for lag screws in withdrawal, for example, it's 12.21. And then when you get into the lateral yield modes, that's going to be in 12.3.
Yep. Good question.
So it's a very good question, and it's unfortunately not a straightforward answer.
Right. So here's another question. What other species of wood are in the NDS supplement?
All right, yeah. So the NDS supplement we talked about, we kind of just hit mostly the big species today, Douglas fir larch, and hem fir and spruce pine fir and southern yellow pine. And those do make up a lot of what folks are using out there these days. But there's a lot of other species that you might come across that are in the NDS supplement. So here's table 4A. I've got up on my screen here. Let me make sure my audience view. I lost it. There it is. Okay. Got it back. I can see what you guys are seeing. So you can see we've got some somewhat more obscure species that you might not come across as frequently. You know, red maple is not necessarily super common, but it's listed in there. So you can see we have literally dozens of North American species listed in table 4A, and then let's see, we have, oh geez, here we go, table, here we go. Let's see, my computer's being a little
wigging out.
Yeah, it's being a little, everybody's refusing to work at this point in the day, I think. Here we go. Table 4F is our non-North American visually graded dimension lumber. So you can see there's Austrian spruce, European species, South Africa, and various others that come from all around the world. So there's also tables in here for North American lumber that's machine graded. So that would be either MSR, machine stress rated, or MEL, machine evaluated lumber. There's tabulated grade values listed for those as well. So we do have quite a variety of design values listed in the NDS supplement for both solid sawn lumber and glue laminated timber.
Cool. Okay, so what are you okay with 2 more questions or 1 more question?
Yeah,
and then bring
Marcia as long as people want to keep asking.
Okay, so we have another question about which member is the main member in a double shear connection?
That's a good question. So in a double, so both of the examples we did today, let's see, were considered single shear, or I'm sorry, we only did one shear example, but that was a single shear connection. So that means we only have one shear plane. So that's this where these two members meet that are being connected. This is our shear plane here. A double shear connection would be, for example, if we had another member on the other side here that was kind of sandwiching this. So in that sandwich kind of analogy, the main member is in the middle and you have the two side members on the outside.
Okay,
so the double shear indicates that there are two shear planes. There would be a shear plane where each member meets.
Right. So if this connection here, say if the 3/4 went to 3 inches, which is the main member? So the 3/4 inch.
So this is a single shear connection. So for this example, the main member for nails, it's very straightforward. The main member is the member that has the point. It has the tip of the fastener. So so for something like this, it's pretty straightforward. When you have something like a through bolted connection where both members are around the same size, it becomes a little less straightforward.
Yeah, it's not dependent on the thickness of the member. It's, I think, dependent on
Right,
how the load's applied, right?
right, right.
Okay, let's see. Here's another one. CLT connections and design examples. Is there
Yeah,
anything
so
coming down the pike on that, or?
gee, that's a nice segue to plug our upcoming webinar that we're planning for July this summer. That's going to include some connection design examples for cross-laminated timber and mass timber connections. So there may be some examples out there from some different manufacturers, especially manufacturers of proprietary products, but we'll be doing our first CLT only connections webinar in July. So everybody keep an eye out on your inbox for an update on that.
Yeah. Okay, we'll have one more question and then we'll bring in Marcy to close us out.
All right, sounds
So
good.
the last question, something near and dear to your heart, is what is the most asked help desk question?
I don't know that there's just one that's most commonly asked. We have a lot of folks that do ask questions related to using proprietary products or using something that, for example, that an assembly that might not be specified for a diaphragm in the special design provisions for wind and seismic, or sometimes you might hear us call it SPIDWIS.
Yep.
So if you're using something that's outside the standard, is that allowed? Yes, it is allowed. There's language in the NDS and the IBC that allow for using these non-standardized materials. You just have to provide either a document from the manufacturer or some sort of third-party certification that shows that the design values of the material, the design properties, the pertinent information that you would need to use it as a design substitute for a standardized assembly or product.